All right, so from now until the end of the year, okay, the tail end's in sight. There's light at the end of the tunnel. From now until the end of the year, we're going to be talking about trig. Remember, the name of this class is Pre-Calc/Trig. Okay, we're now entering the trig part. And I know all of us have been exposed to trig before, like sine, cosine, and tangent, but it probably has been a while. You probably first introduced or first learned about them in geometry, which was probably 2 years ago. Maybe some of you used them in Algebra 2 a little bit last year. Maybe you didn't, but it's probably been a while. So what we're going to do today is kind of bring back our base knowledge of these trig functions and trig ratios, and then we're just going to dive deeper and deeper and deeper into them the rest of the year. Okay, so I just want to know, what is our base knowledge that we're starting with these trig functions? What do you remember about them? How do you use them? Is there a way you can remember which one is which? I just want to get some understanding about what we already know. I don't want to bore you and go over certain things if we already know that or know them. Anybody? Yeah? SOHCAHTOA. Does that sound familiar? Maybe you've heard that before. Sometimes I refer to that as the Indian princess of math. Okay, SOHCAHTOA, because to me it kind of sounds like Sacagawea. From social studies, but it's SOHCAHTOA. So we're going to go ahead and write that up at the top here. You can write it out linearly, like in a line. SOHCAHTOA. But sometimes I notice that students kind of get the trig fractions or ratios confused if we always write it out like that. So sometimes this is how I write it out. I'll show you how I do this. So I do a big S and then O over H for the so part, and then ka, and then toa. Do you kind of know why I write it like that? Yeah? Which side is over which? Exactly. So the S stands for sine, C is cosine, T is tangent. I think we're familiar with those. But whenever we're using a right triangle, okay, it has to have a 90 degree, we can show a relationship between the sides, okay, some type of ratio, aka fraction. So the sine ratio is the opposite side of the angle that you are referencing over the hypotenuse, which is the side opposite the 90 degree angle, okay, the longest side in a right triangle. And then cosine is opposite over hypotenuse, and tangent is opposite over adjacent. We've heard of SOHCAHTOA before. We're familiar with that. Okay. Are we familiar with some common angle variables or symbols? We're used to X, okay, but when we're referencing an angle, those take on a different variable look to them. Yeah. Theta, yeah, okay, so theta, T-H-E-T-A, is kind of a circle with a line through it. Okay, it's a Greek letter, theta. You also might see alpha, which is kind of, I guess, a half of an infinity sign, or like an old school fish that you used to draw when maybe you were little. Okay, that's alpha. And you, bless you. And you might also see beta. Beta has like a long stem on it, and then the B shape. So theta, alpha, and beta are common angle variables. Okay, so we're just going to practice labeling the sine, cosine, and tangent ratios, and then we're going to get into three new trig functions that you probably haven't heard of before, but they are related to sine, cosine, and tangent. So let's go ahead and take a look at this first ratio. So we want to figure out the sine ratio to letter A. So this is the angle that you can think about where we're starting or where we're standing. We want to figure out what is the opposite leg over the hypotenuse leg. Now in this example or this picture, notice how the sides are not labeled, but the angles are. We have capital A, capital B, and capital C. How we can denote side, not measurements, but side labels is if this is angle A, the side opposite it will label as little a. And then very similarly, if this is angle B, the side opposite it will label as little b. And then the side opposite big C will label as little c. So now that we have those labels in, can we figure out the opposite leg and the hypotenuse leg if we're standing at angle A? Can we figure out the opposite side, like what's directly across from it, and then what's the hypotenuse? What do you think, Marie? There you go. So if we're standing at this angle, the side opposite it is little a, so that's the O for opposite. And then the hypotenuse is always opposite that 90-degree angle, which would be C. So the ratio for this sine of angle A, because that's where we're standing, would be A over C. All right, let's try cosine. So according to SOHCAHTOA, cosine is the adjacent, meaning the side next to the angle, over the hypotenuse. So if we're standing at angle A, what's the side next to it, and then what's the hypotenuse? You want to keep going, Marie? Go ahead. B over C. Good. So the side next to A is right there for B, and the hypotenuse again is always C. All right, let's try tangent of A. So SOHCAHTOA, tangent, we need the opposite side over the adjacent. Again, we're standing at angle A. Can we label the ratio? Yeah.
A over B.
A over B. Opposite A, adjacent B. Good. Okay, so those are the three trig ratios if we were standing at angle A. Let's try and take a look at them again, sine, cosine, and tangent, but this time we'll stand at angle B. Okay, so we're standing over here now. What's the sine ratio for angle B? Remember, sine, we need opposite over hypotenuse. What do you think, Maddie? There, B over C. Good. Opposite would be B, hypotenuse, always C. At least in this example, always C. What about the cosine ratio? Good. Keep going, Maddie. A over C. Good. And then tangent? Yeah. B over A. Good. Okay. So notice how the ratios change depending on the angle that you're using, or you can think about the angle where you're standing, because the sine ratio for A is different than the sine ratio for B because you're standing or you're using a different angle. But take a look at this. Notice how the sine angle for A was the exact same as the cosine angle for B, right? Weren't they both A over C? Okay, so there's a kind of neat connection there. Notice how A and B would be considered complementary angles, okay, a little vocabulary word from geometry, because they add together to give you 90 degrees. So there's just a little tidbit, interesting fact there. We can say the sine and cosine ratios for complementary angles are the same. Is it coming back to us a little bit from geometry or algebra 2? Okay, sine, cosine, tangent. Okay, let's talk about three new trig functions. Maybe you've heard of these, maybe you haven't. So sine, cosine, and tangent are the three kind of most commonly used ones. That's why they're the ones that you kind of learn about first. But there are three other ones. We have secant, which is abbreviated SEC. Okay, there's that symbol for theta again. Okay, theta is just representing an angle. And secant, by definition, is the reciprocal of cosine. We have another trig function called cosecant, abbreviated CSC, and that's defined to be the reciprocal of sine. And then cotangent, abbreviated COT, is the reciprocal of tangent. Okay, so we have the three main ones, sine, cosine, and tangent, but then if we reciprocate them, aka flip them, we have these three new trig functions, secant, cosecant, and cotangent. So let's go ahead and practice these. If we are standing at angle A, okay, somewhere right there, we need the reciprocal of sine. Okay, cosecant is the reciprocal of sine. So instead of opposite over hypotenuse, we need hypotenuse over opposite. Now we already labeled what the sine ratio was. Can we use that to figure out the cosecant ratio? What would we have to do with that A and the C? Yeah. We're going to flip it. It's a reciprocal. So the cosecant of angle A would be side C over side A. That hypotenuse side over the opposite. Okay, so these three new ones are just the reciprocal, aka the flip, of the three main ones that we're already familiar with. All right, so very similarly, secant is the reciprocal of cosine. If cosine of angle A was B over C, then secant of angle A should be C over B. We're going to flip it. Same thing with cotangent. If tangent of angle A was A over B, then cotangent of angle A would be B over A. We're going to flip it. I think you guys can fill in the rest of them. Are we okay with those three new ones? Okay, they're not too complicated. I know the words might be a little new to us because we're used to sine, cosine, and tangent, but the idea I think is simple. It's just a reciprocal. Okay? So let's go ahead and today and tomorrow we're going to explore how we can use these trig functions to help us solve triangles. We can figure out every single angle measurement, every single side measurement, and then we're going to get, like I said, a little bit more deeper into these trig functions as the year continues. Okay, so take a look at the triangle at the bottom. We're going to use the trig ratios to figure out some missing side lengths. So in the first one, they're telling us if side CB had a length of 5, what do you think the side of AC would be? Can we think about what kind of triangle this is? If we have a 90-degree angle and a 45-degree angle, can we fill in what that missing angle of A would be? Yeah. That'd be 45 as well. Okay. So maybe we can figure out the side for AC off the top of our heads if we use some type of logic. If we're not keen into that just yet, we can go ahead and use a trig ratio. Do we have a guess as to what a side length AC might be? Maybe not. Let's use a trig ratio, okay? So we know what this side is. That's 40, or that's a side length of 5. And we're trying to figure out this side length. So maybe we'll label that as a question mark. Or, since this side is opposite angle B, maybe we'll label it as little b. Can we set up a trig ratio, because we know some angles and we know one of the sides? How can we use those to help us figure out the missing side? What do you think, Manny? Okay, so tangent of what? Do you want to use angle A or angle B? It doesn't really matter. You want to use angle A. Okay, so if we're standing, we're going to use at angle A. Tangent of 45 degrees Notice how in the table at the top, it was always sine of an angle, cosine of an angle, tangent of an angle. Okay, again, theta means angle. So tangent of 45, we would need the opposite side, which was that length of 5 that they told us, over the adjacent side, which was b. Okay, so this is when we're going to need our calculator, because we're going to go ahead and type in tangent of 45. Now, the first thing I want you to do is make sure that we're in the correct mode. Bless you. Go ahead and hit the mode button next to the blue second button. And in the third row, notice how it says radian, and then next to that it says degree. Okay? We're going to talk about what a radian is later this year, probably next week or so. But for right now, notice how our angles are measured in degrees. 45 degrees. So we have to make sure that that setting is selected. Go ahead over so that it's blinking and hit enter. All right. Just like you have two different ways to measure temperature, like Fahrenheit and Celsius, there's two different ways to measure an angle. You can use degrees or radians. Okay, but we'll talk about radians later. We're probably used to degrees though. All right, so on our calculator, we'll go ahead and hit the tangent button, which is kind of by the division sign. And then inside that tangent, okay, the argument, very similar to the log functions that we just wrapped up, the argument inside those parentheses is that 45 degree. So we'll type in tangent of 45, and it looks like we get 1. Can we solve for b? Yeah. 5. Yep, we can multiply that b over, and we'll get 5. All right, so maybe we'll go ahead and label that on our picture. AC is 5. Does that make sense to us? Can we think about why that side should be 5 based off of the type of triangle that we had? What do you see, Rebecca? Yeah? Exactly, it's isosceles. So geometry terminology, isosceles means two congruent angles, aka two congruent sides. So if this was a 45-45 triangle, it had two 45 degrees, the sides opposite those angles should be the same as well. So if this one was 5, this one should be 5 as well. That's why I was kind of hinting at, do we know it off the top of our heads? But if you don't, you can always use trig to kind of confirm that. All right, let's try the next one. If AC is 5, okay, we already confirmed that. Find the length of AB, which is the hypotenuse in this case. Maybe we'll label it C. So what trig function might you want to use to help us find the hypotenuse? If you think about SOHCAHTOA, okay, if we're trying to figure out a hypotenuse, we basically have two options. We can use a sine ratio or a cosine ratio, because both of those involve the h, okay, the hypotenuse. Which one do we want to use? Good, Marie? We can use cosine. Yep, you have options. You can use either one, but let's go ahead and use sine. Did you say sine? You said cosine. I'm sorry. Okay, we'll use cosine. So do you want to use angle A or angle B? Angle A. Okay, so cosine of angle A, which was 45 degrees. Cosine is the adjacent side, which we found was 5, over the hypotenuse, which is C. All right, so on our calculator, we'll type in cosine of 45. We'll get 0.707. And let's see, to solve for C, we can probably multiply the C over. And then we got to divide by 0.707. .07. Lots of sevens going on. Yeah. You could do that, okay? That would be another way to figure it out because we know 2 of the legs. You could figure out the hypotenuse, okay? The directions said use trig ratios, but that would be another method if you wanted to double check it, okay? But that could definitely work. All right, so let's go ahead and we'll fill in 7.07, all right? So notice how we just completely solved this triangle. We know every single side and we know every single angle. But this last block, we're going to take a look at some unique relationship here. If we were to multiply CB, which we said was 5, by the square root of 2, what would we get? Can we do that on our calculator? Yeah. We got the hypotenuse, 7.07. Interesting. Okay, we'll reference or we'll talk about that relationship in a little bit. Okay, so but keep that in the back of our head. Let's try to do another one. Okay, very similar to the previous one. This time instead of a 45, 45, 90 triangle, we have a 30-degree angle, a 90-degree angle. So what does that make angle A? Yeah? Not quite. 45, 45, and 90 add up to 180. So just because these were the same, not necessarily those are going to be the same. Yeah? 60, right. There's 180 degrees in a triangle. Okay? So let's solve this triangle. If AC is 5, find the length of CB. We'll label that little a because it's opposite angle A. Now this one most likely or definitely won't be 5 because notice how this is not an isosceles triangle. Okay, we don't have 2 angles the same, therefore 2 sides will not be the same. So all different angles means all different sides. So this time we have no choice but to use a trig function. Which one do you want to use in this case? Think about which angle do you want to use first. Do you want to use angle A or angle B? And then in relation to that angle, what sides do you know? Yeah?
Can you do A and then tangent?
Sure, okay. So if we do angle A, we'll have tangent of 60 degrees, and we need the opposite side over the adjacent side. So if we're using angle A, the opposite side would be little a, and the adjacent side would be 5. All right, so on our calculator, we'll type in tangent of 60. We'll get 1.732. And then to solve for A, we got to multiply that by 5. We get 8.66. So maybe we'll label that on our triangle. Alright, last thing about this triangle we got to figure out is the hypotenuse. We'll label that little c. You know 2 sides, so you could use the Pythagorean theorem, or you can go ahead and use trig. Okay, we have some options. Again, if AC is 5, find the length of AB. So you first got to think about which angle do you want to use, and then which trig function could you use based off the sides that you know. So let's pick an angle. Do we want to use angle A or angle B? Yeah?
Angle A with cosine.
Okay, so we could do cosine of A. That would be 5 over C. But you could also use sine, because sine of angle A would be 8.66 over C. Notice how we already know that side. So you do have options. Maybe we'll use cosine. So cosine of 60 degrees, we said it would be 5 over C. On our calculator, we'll do cosine of 60. Looks like we get a half. We can multiply the C over. And then divide by a half, aka multiply by 2. Looks like we get 10. So we'll go ahead and fill that in for our hypotenuse. All right, so we completely solved that triangle. We know every single angle and every single side. Let's take a look at some kind of interesting connection or relationship with this triangle. If we were to take AC, which was that length of 5, and multiply it by the square root of 3, what would we get? Yeah? 8.66. Notice how that was length CB, or the base of that triangle. What if we were to take AC times 2? That would be 10. That would be the hypotenuse of our triangle. So in these two examples, we kind of had some shortcuts, perhaps. These are considered two of the basic, kind of most important right triangles that you could ever analyze or critique. We could have a 45-45-90 triangle or a 30-60-90 triangle. Okay, we're going to talk a lot more about those as we go through this year. And since these are two important or special ones, we notice how they have kind of these shortcut methods. So we're going to talk about those little shortcuts on the back. So if you have a 45-45-90 degree triangle, we notice how two of the sides would be the same, okay, specifically the ones opposite the 45. But the one opposite the 90 degree angle was just off by a factor of square root of 2, okay, some multiplier that we noticed. So in a basic sense, we kind of have this scale factor we could use. If we know one of the sides, we could use the relationship of 1 to 1 to the square root of 2 to help us figure out some of the other sides. So the lengths of the two legs opposite the 45 are always congruent. I'm not saying that they're always going to be 1. I'm just saying that this is kind of your scale factor. If you know one side opposite of 45, you can multiply it by 1, and that would give you the other side. Thank you. Who are we looking for?
You.
Me. Thank you. All right. If we know one of the sides opposite a 45 degree angle, we can multiply it by the square root of 2, and that would give us the length of the hypotenuse. Isn't that what we saw on the previous page? If we multiplied a leg by square root of 2, we got the hypotenuse. Okay, so let's do an example. Let's say if the side opposite a 45 degree angle is 9, then the other two sides are what? Can we figure it out? Yeah.
9
And 9, okay, so I didn't mean to use a comma there. 9 and 9 square roots of 2, okay? It's just off by a multiplier, okay? The 1, and the square root of 2 are your multipliers, aka kind of your scale factor between the sides. Okay, and the other special type of right triangle we can have is 30-60-90. This one, it wasn't as simple, just 1 square root of 2. We had some different multipliers. We had 1 square root of 3 and 2. So we notice that the leg, or the length of the hypotenuse, was twice the length of the shorter leg. Okay, that's the one opposite the 30 degree angle, because the 30 degree is the shortest angle. It should produce the shortest side. And then the length of the longer leg, okay, aka the 60 degree angle, is the shorter leg multiplied by the square root of 3. We saw that in the last example. So let's try another example here. If the side opposite a, let's say, 90 degree angle is 18, then the other two sides are what? Okay, we're going to assume this is a 30, 60, 90. So if we know the hypotenuse is 18, let's figure out the two legs. What do you think?
9 squared 16.
How'd you get that? Yeah?
Divide 18 by 2.
Okay, so if we know the side opposite the 90-degree angle is 18, that was double the length of the 30-degree side. So we can simply divide it by 2 to figure out the 30-degree side. That would give us the 9. And if the 30-degree side is 9, we would have to multiply that by the square root of 3 to get the 60-degree side. So the other side would be 9 square roots of 3. Okay, so no trig is necessarily needed if you have a 45, 45, 90 or a 30, 60, 90. If you have one of the sides, you can figure out the other two just by using these relationships. I'm not saying you have to use these relationships because in some cases we might forget about them, but trig is always a good backup. Okay, if you're more familiar with trig than these special relationships, you can use trig every single time. Okay, so again, just to get used to using trig and solving triangles, we're going to try to get these two done before the bell rings. Okay, so we're going to solve each triangle. That means figure out every single angle and every single side. We do not know if the first one is a 45, 45, 90 or 30, 60, 90 because they don't give us any of the other angles. And in the second example, we definitely know it's not a 45, 45, 90 or a 30, 60, 90 because they gave us one of the angles and it was 43. So we have no choice but to use trig for these two. Let's go ahead and label what we know. So AC was 11, BC was 16. What do we want to figure out first? Do we want to figure out an angle? Do we want to figure out the third side? Up to you. Yeah.
Started setting it up and figuring out angle A.
Okay, so let's go ahead and think about angle A. Maybe we'll figure that one out first. So if you want to figure out angle A, notice how we labeled the opposite side and the adjacent. So which trig function did you use, Tori? Tangent. All right. So tangent of angle A is 16 over 11. Now, if we're trying to figure out angle A, that means we have to move over the tangent function. How do we do that? Keep in mind, this is not tangent times A, so you can't divide tangent. That's not algebraically appropriate. Do we know how to move over a trig function? Yeah, Rebecca? Okay, you see how the tangent button right above it says tangent with a little -1 on it? That little -1 means inverse, aka opposite operation. So when you move the tangent to the other side, it becomes that inverse. Just like how we moved a log, it became an exponential, aka the inverse. If you move an exponential, it becomes a log, aka an inverse. Same thing going on here. So on your calculator, you got to type in tangent inverse, and then your argument would be 16 over 11. Can we get our angle measurement? Yeah? 55.5, okay. Or 49, yep. However you want to round, that's fine. All right, so now that we know what angle A is, do you think we can figure out angle B fairly quickly? If there's 180 degrees in a triangle, good, Marie? 34.5, good. All right, so the only other side that any other piece of information we got to figure out is the last side. You could use Pythagorean theorem, okay, if you're comfortable with that, a squared plus b squared equals c squared, or we can use trig. We got to figure out that hypotenuse. What do you want to try? What do you think, Marie? Go ahead. We could use sine or cosine. All right, so pick an angle, either A or B. You cannot pick the 90-degree angle when you're using these trig functions. That's kind of off limits. Okay, you have to pick one of the other two. So do we want to use angle A or angle B? Do we have a preference? Yeah. A, okay. So if we're going to use angle A or stand at angle A, we can either use sine, because that would be 16 over C, or we could use cosine, that would be 11 over C. So you have some options. Maybe we'll use sine. So sine of 55.5 is 16 over C. Let's see, on our calculator, sine of 55.5, we have 0.824. We can multiply the C over, and then divide that decimal. Say 19.41, or however many decimals you want to round to. If you were to use the Pythagorean theorem, you should get something relatively close to that. We're doing okay? Trig coming back to us, I hope. If not, if not from today, definitely by tomorrow or by the end of this week, because we're going to be doing it the rest of the year. Okay? We're going to stop there for today. We'll save the last one as kind of a refresher for tomorrow.